So I think it's time to start. I would like to welcome you at our seminar. We have the pleasure today to have Professor Sylvia Fruhwirth Schnatter with us. Professor Sylvia is a professor of applied statistics and econometrics at the University of Economics and Business at Vienna, Austria. She's a past president of International Society of Bayesian Analysis, and her research interests include Bayesian and computational statistics, MCMC methods, econometrics, among others. On a more personal note, her contributions on finite mixture modeling were highly influential for me during my PhD years and beyond. So it's a real pleasure that Professor Sylvia is here with us today. So I would like to welcome you on our research seminar, and you can start your presentation.
Thank you so much for this really kind invitation. It's a great pleasure for me to give the presentation today, which was supposed to take place at the European Young Statistician meeting, and for technical issues at Sorbonne University in Paris, where I was staying at that time, didn't work out. So it's very nice to finally have the opportunity to talk about recent work we have been doing with mixture models. And this is work together with Gertraud, Martina Valli, Bettina Grün, and PhD students of ours, Jan Greve, and we are all now together at the University of Business and Economics in Austria. So, okay. Now I can't switch forward. I was expecting some technical troubles. So, presentation beginnen. Okay, now the slides are gone. So now it's like I'm having kind of bad luck. Okay, now it's working. Okay.
Yeah, now we can see your slides again.
Yeah. So when you talk with PhD students or other colleagues about mixtures, there are some kind of common questions you receive. So there is a quote by Larry Wasserman. Christian Robert discovered this on his blog. It's now no longer active. But Larry, for instance, thinks that a mixture like tequila are really evil and you should avoid them at all costs. So the question is this kind of true? Okay, now I can't move on again. So maybe übertragen Sie eine Steuerung. But it was working when we tried it before.
Yes, I really don't know what happens now. Maybe you can just give it one more try to start again the presentation.
This usually doesn't happen. This, I don't know. What? You have the slides here.
Could it be that Larry was correct, that you are talking for mixtures and this is evil?
I didn't understand you. Okay. No. Can you see the slides now?
We can see actually your screen now, your whole screen.
Because I'm sharing my screen, and here are the slides.
Now we can see your slides and they are moving.
They're moving. Okay, so maybe if I go to full screen, let me see if it's working if I go to full screen. Okay, now they are moving. Yeah. I'm really sorry about that. So let's hope
so pictures are really evil things.
We don't want to cancel the seminar a second time. So maybe mixtures after all are evil.
Yeah.
To a certain degree. So when you talk to people, they often wonder whether the number of components have to be known when you want to use finite mixtures, in particular for clustering. And if that's not the case, whether you have to implement one of these complicated trans-dimensional MCMC samplers, reverse jump, for instance. And if you're familiar with all this literature on Bayesian non-parametric mixtures, which allow to have infinite components, they are very, very popular. And there is like this perception that when you use one particular interesting example is the Dirichlet process mixture. So if you use this kind of mixtures, there's a kind of a perception that these are more flexible than finite mixtures. So the question is this actually the case? And spoiler alert, the answer to any of these questions is going to be no. And I want to convince you that finite mixtures, if you put it up in a right manner, if you do a Bayesian inference here, are a tool that are very flexible, and the most recent model that we are investigating is even more flexible than the well-known Dirichlet process prior. So here's the outline of the talk. I will briefly recap what mixture models are doing in Bayesian cluster analysis. And then I will present the most general, most recent work we have been doing with finite mixtures. It's a paper that was just accepted to appear in Bayesian analysis. The core of the presentation will be a computational technique to estimate mixtures where the number of components is unknown. We call it telescoping sampler. And it's not going to be a reversible jump MCMC algorithm. It is a surprisingly simple Gibbs sampler. So the good news is already here. Even if you don't know K, we suggest a sampler that is very easy to implement. I will have a few brief examples. And if time permits, then I will show you how what we are doing here is related to Bayesian non-parametric mixtures. So just to set up the notation here, so this is what you see here, the definition of a mixture distribution. So the observations are denoted by yi, and we describe the density here as the linear combination of component density. So the theta k will be a generic expression for the parameter in each component. The eta k is the weight distribution, and the k is the number of components. For simplicity, we assume that the component densities arise from the same distribution. That doesn't have to be the case, so the theta varies over the components. And a lot of the talk will focus on the components' weights and how to model them in a Bayesian framework. So mixtures, when you apply them in the context of clustering, mean unsupervised clustering, so group membership of the observations is unknown. Maybe I'm going to reduce the little window here. And for this aim, latent allocation variables are introduced for each of the observations. This is a categorical variable taking one of the k components here. And then it's well known when you condition on this component indicator knowing that it's equal to k, then you have this conditional distribution being equal to the component density here. And the prior distribution here, of course, corresponds to the weight distribution. So this is all well known. And now I can't move anymore again. I don't know what's going on here.
It's again the same problem?
It's the same problem again.
Maybe you can try to undo the full screen.
Okay, I can't even leave the full screen anymore. Okay.
Now I can see the
now
next
I can see. Okay, so maybe this is something that happens at random moments. So seems like you have to live with that. I'm really kind of confused by the fact that it is related to presenting in Athens. So in case you are not so familiar with mixture models, of course, there is the classic book I wrote a long time ago. And there is this really nice recent handbook of mixture analysis that I did together with Christian Robert and Gilles Deleu, and Dimitris contributed a chapter, so there are contributions from 35 scientists who have been working in mixture analysis for a long time, and I think it gives you a broad overview of all the aspects of mixture analysis. So let me go back to Bayesian cluster analysis. So you want to partition the data into groups where we think groups observations are similar, more similar than between groups. And it has been known for a long, long time that when you apply a finite mixture model to your data, then clustering arises in a very, very natural way. And we have already introduced this indicator variable SI that indicates to which component an observation belongs. And in this way, the data are clustered here. And you can say two observations belong to the same cluster if these component indicators are identical. So I'm going to use here a very stylized example because obviously in this data are two clusters. And now suppose we fit a mixture with two components. Because these components are well separated, we will be able to identify the two clusters because these observations are assigned the indicator 1 and these observations are assigned the indicator 2. And in this sense, in very general, the indicators, the SIs up to SN, define a partition of the data points here. And I'm going to use this calligraphic C whenever I refer to these partitions for the rest of the talk. So these clusters here contain the indices of those data that belong together. And the number of those clusters will, for the rest of the talk, be denoted by K+. Now, when you think about it, the component indicator, because it's unsupervised clustering, is not known. I mean, this is the reason why we do unsupervised clustering in the first place. Now, with these component indicators being latent, random, when you think about it, that means also the partition is random. The number of clusters is random. And when we do Bayesian inference here, we can look both at the prior distribution that we have on these partitions, for instance, the number of clusters, as well as the posterior distribution that then tells us, given the data, how many clusters do we have, what do the partitions look like, which observations are clustered together. And I will talk a lot about this prior on the partitions and the prior of the number of the clusters, because I think this is something that very often is overlooked in applied mixture analysis. Particularly if you do Bayesian inference, sometimes people still use kind of convenience priors. In a finite mixture context, this is very often a uniform distribution on the weight distribution. And I feel that people should think more carefully how to choose this prior, because as we will see, it can have a huge impact on the prior, on these partitions, and on the prior of the number of the clusters. So I would like to emphasize it's important to distinguish on the one hand side between the number of components, K, that you have in your model, and on the other side, the number of clusters that you have in your data set. This stylized example I've shown before was a situation where the two were the same. So we fitted a mixture with two components to a data set that obviously had two clusters. But that doesn't have to be necessarily the case. So when you fit a mixture with K components to data that have less clusters than K, you have a situation where these two numbers are different. And I think it's important when you use finite mixture modeling to think carefully about whether the model you set up and the prior distributions that you chose are a situation where also a priori the two of them are the same, or whether the number of clusters might be lower than the number of components. So let's return to our stylized example here. Let's say we don't know, it's a very high dimensional situation, so we don't know how many clusters we have. In the data, we fit 5 components, and because this is a stylized example, we can see what would happen. So out of these 5 components, 2 of them are used to cluster the data. And here in this example, the indices are the indices 3 and 4. So the component 3 and 4 are used to cluster, whereas the components 1, 2, and 5 remain empty. And it could well be that instead of the component 5, the component 2 is used for clustering, and the other 3 components remain empty. And I know this is a very simple example, but I hope it shows you that in a situation where you don't know how many clusters you have in the data, you always have to account for the possibility that some components remain empty. And that when you look at the estimated indicators, you can learn and see how many clusters are there, because here, let's say we do MCMC inference, and all the time these guys here get the indicator 4 and these get the indicator 2. Then we see only 2 components are used, and this is what we define as the number of clusters. So there is information in these latent indicators regarding the number of clusters. So let me say a few words, more words about this question. Okay, is the number of data clusters always equal to the number of components? And as statisticians, we can address this also by using the following experiment. So let's say you have allocated the observations to the different components. And now what you can do, you can look at the number of observations allocated to each component. And we know what the distribution is. So these occupation numbers, as I was saying, because the allocation variables SI are latent, these NK are also a priori random, and might also be a posteriori random if you don't have much information in the data. And a priori, they follow a multinomial distribution with the probability distribution here. So the number of observations is the number of experiments, and the probability distributions are the probability distribution you have here in your experiments. And if some of these weights are small, or if you don't have that many data, then we know from multinomial sample that might lead to a situations where we have empty groups, where these indicators are equal to 0. And here you see now the kind of formal definition of what we mean when we say a number of clusters. It is actually the number of non-empty components. So when you have the component indicators, you can work out what the occupation numbers are, and then you can count how many of the components were not used, are empty, and this then defines you the number of the clusters, the number of non-empty components. And when you go back to this thought experiment that can happen anytime with finite data, in particular, some of these weights here are pretty small. So even if the K is fixed, depending on the weight distribution, depending on the number of observations, the number of filled components, number of data clusters, is a random variable and will take values smaller than K with positive probability. Now, when we do Bayesian inference for mixtures, we need priors for all the parameters, and the talk will focus on the prior on the weight distribution. And the common prior here is the Dirichlet prior. And let's consider for the moment a finite mixture with K fixed. Then one assumes a symmetric Dirichlet prior on the weight distribution. And this Dirichlet distribution, so if you have like only like 2 components, it would be a beta distribution with the degrees of freedom. And the Dirichlet is the extension of that. It lives on the unit simplex. And the choice of this hyperparameter very strongly influences where this prior on the weight distribution is concentrated. And here on the left-hand side, it is gamma equal to 4. And you can see here, so this is the first weight, this is the second weight, and the third weight is, of course, 1 minus the sum of the others. So you see when you choose gamma equal to 4, everything is concentrated here in the interior. So when you take 1 minus the sum of these two guys, there is still room left for a third weight to be positive and different from 0. The situation, however, is getting very different when you decrease the hyperparameter. So this would be 0.05, because now you can see already a priori the Dirichlet distribution lives on the boundary of this unit simplex. And what that means is that there isn't room for 3 positive weights. So here would be a distribution where a priori one of the weights is already equal to 0. And the smaller you choose this value, the more you even concentrate on the corners of this simplex, which means one of the weights is very close to 1 and the other are more or less equal to 0. And now in combination with the experiment I have been explaining before, so if I have a prior that already encourages weights that are close to 0, then when I do this multinomial experiment, I have a high probability that the number of data clusters already a priori will be smaller than k. And this whole strategy underlies the work Gertrud, Bettina, and I have been doing in the area of sparse finite mixtures to a small value of gamma, because as you can see here, for the example of 100 data points where you choose k equal to 10 fixed, by choosing a small hyperparameter, and this is the whole idea of sparse finite mixtures, you have already a priori, so the k plus the number of non-empty components is a random variable, and this would be the prior distribution. And in this way, when you combine the prior distribution with the information in the data, you get a posterior distribution of the number of clusters. And the important point here is that you have to choose a small hyperparameter, because as you can see, if you increase the gamma here would be gamma equal to 4, and you choose 10 components, then already a priori there's a high probability that the number of data clusters will remain the same. This is was kind of the state of the art of the work of the last years. And what we have been now doing recently is using this framework of sparse finite mixtures and make the k random and unknown, which brings us to our recent work. Yeah, I think I already explained this. So as I was saying, I think this is a kind of a summary of the most important point. It is important to distinguish between a number of components and a number of clusters. And as I was saying, in the framework of sparse finite mixtures, we fix the k, but in applied mixture analysis, you don't know the k actually, and you would like to assume that both the number of components and the data clusters is unknown and have to be estimated from the data. And taking a Bayesian perspective, the most natural approach, of course, is to treat them as unknown parameters and to put priors on them. And what is now interesting in this framework is, and this is what people have been doing when they have mixtures where k is unknown, you put an explicit prior on k, and this is also the strategy that we are following here. And by doing so, and then you have an explicit prior on the weight distribution, and as I explained previously, by doing so, by choosing the prior on k explicitly, by choosing a prior on the weight distribution, you define a prior on the number of data clusters implicitly through these choices. And this is something that should be kept in mind. So let me continue with discussing what we now call the generalized mixture finite mixture model. It is basically a mixture model where k is unknown with a fine twist that I'm going to explain in a minute. And as I was saying, the paper was just accepted in Bayesian analysis. So down there we have the definition of the mixture model. So we have seen this before, and then we put priors on all the unknowns. So there is a prior on the component parameter. There might be a hyperparameter, so they might be a hierarchical prior, so they share some unknown hyperparameter. Then we have this multinomial distribution on the component indicators, and then we have the Dirichlet prior on the weight distribution. Finally, we have the prior on K. Now, it's a very generic framework, so there are no restrictions on the parametric family. Could be discrete, could be continuous, multivariate, time series, whatever. The observation, so it's like any mixture model, a very general framework. It could be, there's no restrictions on the prior on K here, so it could even be, we are including here the framework of sparse finite mixture, where we have a Dirac measure on a fixed value, or even Dirichlet process prior, where you choose the K to be infinite. And in this whole framework, people have been working on this, how to choose all these ingredients here. What we focus in this work on is what I marked here red. There's one additional model choice that you have to make, and this is the choice of the hyperparameter in the Dirichlet prior. And this is what we investigated in much detail here, because this is part of the specification of the model, how to choose the hyperparameters in this Dirichlet prior. And what we are doing here is that we, in principle, allow this hyperparameter to change in dependence of the K. So this is why we call it a generalized mixture of finite mixture models. So it can either be a fixed value or it can depend on K. In the paper, we formulate this as this very generic framework, but then we consider two special cases. One where this hyperparameter is fixed. Very often it is assumed to be equal to 1, because as I was saying, this gives you a uniform distribution on the unit simplex, and people think by choosing this uniform prior, they are agnostic. They don't input any influence here, and as we see, that is not necessarily true. So this brings us back to the famous mixture with K unknown in the Richardson-Green paper, where they introduced the reversible jump MCMC. And there is a paper by Miller and Harrison in JASA in 2018 that gained a lot of attention, and also in that paper they fixed this hyperparameter. So we call this the static mixture finite mixture model. And then we look at a second special case, which we call a dynamic mixture finite mixture model, where we have fixed hyperparameter, and the parameter in the Dirichlet distribution is then defined as this hyperparameter divided by K. So the larger the K is, the smaller this hyperparameter is going to be. And when you think back what I explained like 10 minutes ago, the smaller the hyperparameter, the smaller the number of clusters compared to K. So this is a definition that kind of protects you against overfitting the number of clusters. So we came across this definition just by starting with mixtures, sparse finite mixtures, dynamic sparse finite mixtures, and then we made K random. During the reviewing process, we realized that this model has been also used and investigated by other people. This very nice paper by McCulloch and Young, for instance, and also in other papers. So static mixtures where the hyperparameter is fixed, and dynamic mixtures where the hyperparameter decreases in the manner you see here. Now, as I was saying in the very beginning, it is important when you do finite mixture analysis to think more carefully about the implication of the prior choices regarding the weight distribution. So I'm going to discuss a bit the prior distribution on the partitions here. And it's a partition, as we have seen before, is characterized by the number of clusters and the occupation numbers. And these are here the sufficient statistics that you need for formulating the prior distribution. And it is very easy and has been well known how to derive this prior in the situation of a static finite mixture. So as we have seen, a certain sequence of indicators define a clustering. The prior probability depends here on the weight distribution. We integrate over the weight distribution. And this term here is then all the different possibilities that different sequences of indicator define the same partition, as we have seen for this very stylized example. So different sequences of indicators define the same partition, and this term accounts for that. Now, taking this now to our generalized finite mixture, when the k is fixed, this is easy. So even if the hyperparameter depends on the k, we show this in the paper, but it is kind of obvious here, we can say what is the prior distribution of a specific partition given the k and given these hyperparameters. And this is going to be the most important ingredient then for our telescoping sampler. So we are going to use this prior distribution on a specific partition for a given number of components and for given hyperparameters to derive the posterior distribution of the k given the data. So we are not going to use any reversible jump MCMC, as I was saying. We are going to use exactly this EPPF here. So this is a slide that maybe I'm going to need later on when I make the connection to Bayesian nonparametric methods. So what I've shown on the previous slide was for a fixed k. So this is just a different way to write it down. So when you know the k, you have a so-called Gibbs type prior. It's a term from Bayesian nonparametric. And when we now introduce a prior on k, then we end up with a prior that is more general than a Gibbs type prior. So we obtain something that is more general than, for instance, a Dirichlet process prior or a Pitman-Yor process mixture. Okay, so we discuss in the paper also how we obtain the prior on the number of clusters. That is kind of challenging because it basically means you have to sum over all the partitions that define the same number of clusters. What we do in the paper, we solve this combinatorial problem by looking at the prior of the labeled cluster sizes. So we arrange the clusters in an exchangeable order, and then we are able to write down an explicit form for the prior of the number of clusters. And it looks very complicated mathematically. So there are two terms in there that depend on the k. The k is random, so we wait with the prior distribution on k, and the k goes from the current number of clusters to infinity. So you have to work out what the value is of this infinite series here. And we show in the paper how to determine these quantities recursively and work out what the prior on the number of clusters is. So for instance, what you can see here is a comparison between the static mixture where the gamma is equal to 1. As I was saying, this is the traditional mixture with k unknown of Richardson and Green and Miller and Harrison. So here you would see that basically the prior on of components, which is the blue line, and the prior on the number of clusters is roughly the same. These are different prior distributions, and if I have time, I will discuss about that. And then on the other hand, when you move on to a dynamic mixture, then you gain additional flexibility because these two quantities are not necessarily the same, also a priori, and this is what gives you the additional flexibility that we have in these type of mixtures. So here, for instance, let's take as an example, let's even say a uniform distribution on the prior of components. And then we see that even if I have this uniform prior on the number of components for a dynamic mixture, I have a high probability on a moderate size, on a moderate number of clusters here. Whereas the uniform prior on K, which is truncated as 30, would basically allow anything between 1 and 30. And this is another look at the prior distribution of the number of clusters in comparison with the prior expectation of the number of components. So in both figures there are dashed lines, which are the prior expectation of the number of components for different prior distributions. And what the full lines are showing is the prior expectation of the number of clusters in dependence on the hyperparameter, the gamma here. This is a static mixture. So we see what we have seen on the previous figure for gamma like 1, or in my book I recommend gamma equal to 4. You're basically in a situation where the number of data clusters and the number of components is the same, which makes sense. For instance, if you compute marginal likelihoods to choose the number of clusters, you would like to have a situation where the number of components and the number of data clusters is the same, because you use the marginal likelihood for K to choose the K plus. But on the left and right hand side, you see a dynamic mixture. So you see this additional flexibility this model is having, because the prior of the number of clusters is well below the prior of the number of components, but still it is finite because it's of course always smaller than the prior expectation of K. And here for comparison, I'm showing a Dirichlet process mixture where the number of clusters goes up to infinity. And it has been shown by Miller and Harrison, for instance, that when you have a finite number of clusters and you use the Dirichlet process mixture, then of course you have inconsistency for the number of clusters. Whereas there is hope, and we are still not sure whether it's actually true, that you get a consistency estimator for the number of clusters in this framework of dynamic mixtures, because the prior expectation here is always finite and bounded by the expectation of K. Now, if you want to learn more about the implicit prior on the partitions, Jan developed a very nice package that we call the FIP package. The corresponding paper is, I hope, close to be published very soon. We call it Spying on the Indicators here, and it has a very nice functionality. So when you have your specific data set, you know the N, you can then investigate what the choices are of specific prior distributions in a Bayesian mixture analysis, and the paper explains this also very nicely. So how about time? So I'm kind of lost track of time here.
Sylvia, you have, let's say, 15 minutes.
15 minutes, okay, yeah. So based on what I told you so far, we think that this extension to mixtures where K is unknown, and this family that we call dynamic mixture, where the hyperparameter is defined as an unknown hyperparameter divided by K, is very useful. So the question is how to do the estimation here. In the paper, we have a sampler for that situation where we have a dynamic mixture, finite mixture. It also works for static mixtures in certain situations. So I'm going to discuss the corresponding sampler here now for the dynamic mixture, finite mixture model. Because we don't know K, we need a trans-dimensional sampler. And for those of you who are familiar with mixtures, know, of course, reversible jump, MCMC, and Petros once had a PhD student when he was still in Athens, and she had to code reversible jump MCMC from multivariate Gaussian distributions. It's a very nice paper in statistics and computing. But I remember Petros saying it was really hard to make it working. This recent Miller and Harrison paper in JASA, they showed how to use sampling techniques that were developed for Bayesian nonparametric methods, the so-called Chinese restaurant process is one of the representations of the random weight distribution. And there are sampling schemes for that can be applied also to mixtures where K is unknown. Of these two techniques, reversible jump MCMC, which was developed for static mixtures or finite mixtures, can be extended to dynamic mixtures, whereas the Chinese restaurant process, here it would not be possible because you need this marginal EPPF, and that has a complicated form for dynamic mixtures. So these CRP samplers only work for Gibbs type priors. Now this is where our telescoping sampler comes in. It is easy to implement. It's a generic sampler for arbitrary component densities. So we show in the paper you can use it for multivariate Gaussian distributions. You could use it for discrete data. You could even extend this then to a framework, let's say, of model-based clustering of time series. So we'll see in a minute that the only ingredient that we need is this conditional EPPF function. And as I was saying, it is designed specifically for dynamic mixtures of finite mixtures. It also works for static mixtures of finite mixtures, as long as there is a gap between K and K plus. And you will see in a minute why we need this gap. So if you have a hyperparameter gamma that is so large that K and K plus collapse, then you can't use the telescoping sampler. But as long as there is only maybe a tiny difference between the two, you can use it. So as I was saying, we are using the EPPF. The EPPF was the prior distribution on the partitions of a mixture of finite mixtures. So there is some similarity here to Chinese restaurant process sampler. However, those sampler marginalize over the K, whereas we introduce K as a latent random variable, very much as you do in reversible jump MCMC. So you sample the K in reversible jump MCMC, and this is also what we are doing here. What you see here is the most important ingredient for our sampler. This is the posterior distribution of K given the partition. So let's think back, what does this mean? What do I have to know to sample K? I only have to know the sufficient statistics from my partition, which is how many clusters, so how many unknown components, and how many observations in each of the occupied clusters. That's all. These are really the sufficient statistics here. So when you look at the posterior distribution of the number of clusters, it's proportional to, and now you see the EPPF is serving as a likelihood function for K, because in our KIP sampler, we condition here on the current partition on N on K plus, on the occupation numbers multiplied with the prior. And that's all that you're going to need. And as you see here, nothing pops up whether we have Gaussian mixtures, Poisson mixtures, or whatever. It is totally generic. The only parameter that is necessary to sample from this posterior distribution is to know this hyperparameter of the Dirichlet distribution. And even if this is changing, you can use this posterior distribution here. What that means is that this little line here, this little formula here, can be combined with any MCMC algorithm for finite mixtures for a fixed number of components. and can be based on Gibbs sampling, as was shown in the very important paper by Christian and his co-author in 1994. So I don't know, I'm kind of running out of time here, but let me just mention, because it is important to make sure that this sampler is correct mathematically, because it's a transdimensional sampler. These are not trivial samplers here. So what the sampler is doing mathematically here is it switches between sampling in a situation where we sample the latent indicators. So this is like for a given k. So this is like the complete data posterior, conditional on the k. So this is what you always do when you do Bayesian inference in mixture analysis. And then we collapse and move to the partition space here, where we only consider the non-empty components and marginalize over the empty components and the weight distribution and the allocation. So this is where we get kind of close to Bayesian non-parametric, but we are kind of switching forth and back. So in the interest of time, I will be very brief on the MCMC scheme. So as I was saying, we update the partition by sampling the indicators like we do in any finite mixture. The moment we have the indicators, we work out now the sufficient statistics that we need from the partition, the number of occupied components and the occupation numbers. And then we update the parameters only for the field components, and we make sure mathematically that is a valid strategy here. And now comes the important point, and as I'm saying, it's a single line in your sampler here. You sample k conditional on the partition using these sufficient statistics that you have, and now you're done. So basically, we're nearly done, because if the k is bigger than k plus, then you add empty components and sample the parameters from the prior here. So no split, merge and things. It's only like this kind of birth move that is always there, also in a reversible jump MCMC. Okay, so it's like, I don't know, 5 minutes or?
Maybe, yeah, a little bit more than 5. So yeah. You can. Okay,
so maybe so that you see how things are working. We benchmarked our telescoping sampler against reversible jump MCMC in the paper. So here you see a comparison. These are simulated data, 10,000 observations. And here you see the output from the telescoping sampler. So you see gray draws and black draws here. So the gray are the number of components, and the black ones are the number of clusters. And here in comparison, the reversible jump MCMC. With the reversible jump MCMC, split merge moves gives you the K, and then, I mean, you have the number of clusters the moment you have the indicators. So this was not the explicit focus of reversible jump MCMC, but you can get this information. So here you see, when you look at the K, it is the same posterior distribution because we matched priors here. You can see how the telescoping sampler is even moving more quickly than reversible jump MCMC. So the reversible jump only samples the K. The Chinese sample, on the other hand, samples the number of clusters. So in terms of autocorrelation, we are here in this benchmark example doing more or less as good as this Chinese restaurant sampler. And I mean, this is a single move sampler, and we are doing the clustering of the observations all at the same time. So this is a conditional sampler, but that takes me too far into the details of the sampler here.
Excuse me, Sylvia, can I just ask a quick one? So the component-specific densities, in which family they belong in these examples?
Oh, it is, sorry, yeah, it's not on the slides. It's univariate Gaussian distributions.
Okay, so and the reversible job is designed with a standard birth, death, and split and combine moves, I guess.
Yeah, so yeah,
okay.
we are using some old Fortran code from Peter Green here.
I see.
Yeah.
Great.
Yeah, so we didn't code the reversible jump for multivariate mixtures.
Nice.
Yeah, so let me maybe briefly just show the examples from the paper so that you see that it's also working for multivariate Gaussians here. So as I was saying, we recommend to use the dynamic version because it gives you more flexibility. We looked carefully how to choose a prior for the random hyperparameters. So we explain in the paper why we think that this F6 free distribution is a good choice. We also explain in the paper why we think that we need a flexible prior on K. So we use a translated beta negative binomial distribution, which just is a kind of a hierarchical version of a Poisson. So you start out with a Poisson distribution, put a gamma prior on the intensity, and then put a prior on the scale here. And then you end up with the beta negative binomial distribution, which has 3 parameters, is very flexible. And we also argue in the paper why the BNP 134 prior is something that we would recommend in applied mixture analysis. We skip this here. So we were, of course, looking into the galaxy data. We even have a recent nice paper, how many data clusters in the galaxy data set, was motivated by one of the model-based clustering workshops where Adrian said, okay, Bayesian mixture analysis, I'm not sure if it's useful. Sorry. Sorry. There are some tiny flies in my office, and it seems like I swallowed one of them.
Okay, no worries.
It's always at this time of the year the flies come in to be. It's getting cold outside.
Take your time. Take your time.
Yeah. So you can see here the difference between the posterior distribution of the number of clusters and the number of components. And here again, you see this additional flexibility that we do have in the framework of the dynamic mixture of finite mixtures here. So we could recommend to choose the BMP prior, and using that prior, we have very clear evidence that there are 3 clusters in this data set. So maybe I can conclude with the 2 other examples that we do have in the paper. One of them is a standard data set in the clustering community, where we know it's multivariate Gaussian distribution, where we know that there are 3 potential groups. Now here we are fitting a multivariate mixture of Gaussian distributions with K unknown. And the other example is a latent class analysis with K unknown. It's a smaller data set. And also here there's a psychological theory that suggests that we have 2 groups here. So it's a small data set, so we were using this as a benchmark data set to see what we obtain when we use this dynamic mixture, finite mixture with the F prior on the alpha that we recommend, and what we get when we use different priors here. It was very easy and straightforward to estimate a multivariate mixture of Gaussian with K unknown using the telescoping sampler. It was very interesting to see that these data are obviously very informative regarding the number of clusters, because regardless what prior of K we were choosing here, we always got back 3 clusters here. Whereas with the latent class analysis for the sphere data, which are a small data set, using the posterior distribution of the number of clusters was not so robust with respect to the prior on K, but using this recommended choice here of the BMP prior, we've ended up with estimating 2 clusters in this data set. So maybe as a final example here, that telescoping sampler is also working in large data set. The so-called Mozambique data here, 12,000 women were asked which kind of source they use to get information about HIV. So these are 10 binary variables. And again, we are using here latent class analysis, but for a very large data set. So here you can see the first 1,000 draws, in red, then the trace plots of the number of clusters, in blue or gray, rather, the posterior draws of the number of components. Everything works here really kind of nicely. So the posterior distribution, so this would be the prior, this is the posterior distribution, here would indicate 4 clusters, and then you can do the usual searching for an identified solution here. So we condition here then, so we choose the posterior distribution to select the number of clusters, then we do the stratification of the MCMC draws, and then we resolve the label switching issue by doing the point process clustering. So once we have the K+, we are doing exactly what we do in sparse finite mixture analysis. And then you can kind of give an interpretation to the 4 groups, like where women get information from. This would be either the church and the community, or TV, or friends, or the modern women who read radio, hear radio, TV, and news. Okay, so I'm going to switch all this material on PMP. Yeah, so we are working on a nice R package. Jan is working on the nice R package. So coming back to the questions I had in the very beginning, are mixtures evil? No, I still think after working with them for such a long time, they're very interesting and useful. The number of components doesn't have to be known. You can put a prior on K and check implicit priors using the FIP package when you want to see how influential is the prior information that you choose. No, you don't have to implement a complicated reversible jumper MCMC. You can use our telescoping sampler. And if you go back to the paper where we also discussed the relationship to Bayesian non-parametric mixtures, you will see that in particular the dynamic mixture finite mixtures are even more general than Dirichlet process mixtures, and have close connections to a certain class of Pitman-Yor process mixtures in Bayesian non-parametrics. Okay, then thank you very much, and I hope there was something in this presentation that was of interest for you. Thank you very much.
Thank you very much, Sylvia, for a very interesting talk. So let's proceed. Are there any questions for Sylvia? Can I ask a quick one, Sylvia? Have you actually compared with schemes like allocation sampler? I don't know if you can recall this technique.
Yeah, well, I like the allocation sampler very much if you can actually integrate out the parameters.
Of course.
Yeah, so it, like in the latent class analysis example, if you just have like a uniform distribution on the probabilities, it would be possible to set up an allocation sampler. I mean, it is still a one block sampler, because you can only classify an observation based on the indicators of the other observations, whereas we are still using here a conditional sampler. So conditional on the parameters, we are clustering all the observations at the same time. So for instance, with this Mozambique data set where you have 12,000 observations, you would need 12,000 iterations through the allocation sampler. So this is why I think that the allocation sampler has its merits, but it has also its limits in situation where we have very large data set. and in situations where we cannot integrate out all the parameters.
Yeah, of course.
Yeah, and I didn't mention this in details, but for instance, for the multivariate Gaussian distribution, we were using a hierarchical prior. So the hierarchical prior that we introduced when we had this paper on sparse finite Gaussian mixtures. So it's very important with Gaussian mixtures in higher dimensions to have hierarchical priors. So I wouldn't be sure if the allocation sample is, you would have to choose a conjugate prior here for multivariate Gaussian mixtures and fix the parameters, kind of, yeah.
Yeah, of course.
The hyperparameters, yeah. Mm-hmm.
So,
can I ask something?
So, please.
Why is it closer to the Pitman-Yor process, this method? Is it because of the choice of the size-biased weights? Is it, I don't know. Because I've read the paper that you choose in a size-biased way, where, you know, like a stick-breaking formation of the weights.
Yeah. So it is well known. I don't know. Do you still see my slides here?
Yes, we can see them.
Yeah. So when you compare the EPPFs of a finite mixture with a Pitman-Yor process prior, and you have a finite mixture where K is fixed, then it has been shown by Pitman, Canadian. So it has been known for a long time that these two models imply the same EPPF. So they have the same prior distribution on the partitions here. So you can see it here when you have a static finite mixture with a specific gamma, then the corresponding EPPF for K fixed is equal to the EPPF of a Pitman-Yor prior where the enforcement parameter is negative. So if you have Pitman-Yor prior where the enforcement parameter is positive, then we know that we have infinite number of clusters. So this is a whole different family. So the relation between finite mixtures and Pitman-Yor priors is in the situation where the enforcement parameter is negative, because then you end up with a finite number of clusters. And here you see this relation here. So you choose the hyperparameter gamma, you choose the K, and then the corresponding Pitman parameter has the corresponding reinforcement parameter, and the concentration parameter is K times gamma. And when you do this for the dynamic finite mixture model with K still fixed, then you also have a corresponding Pitman-Yor prior. And now what we do in the paper is we have a prior on K. And now the interesting situation here is when you have a static mixture, finite mixtures where the gamma is fixed. So when you integrate over the K, then you end up with something where you mix over the concentration parameter, which still gives you a Gibbs type prior. So there's very interesting work by Igor and his co-authors, Igor Brünster, where they show this. But the interesting thing is when you take a dynamic mixture, finite mixture parameters, then you don't mix over the concentration parameter, but you mix over the reinforcement parameter. And that yields a model that is beyond the class of Gibbs type priors. So you end up with a generalization in a certain sense of the Dirichlet process mixture. So if you're in the dynamic mixture of finite mixtures, if you put all the prior information on K on infinity, then you get back the Dirichlet process mixture. But because we assume that K has a distribution, we obtain something that is kind of related to Dirichlet process mixture, but more general. Yeah. So sorry for the long answer. There was no short answer to the question. I hope it clarified.
Oh.
So I see John asking a question.
Hello, Sylvia. Yes.
Hi, John. Good to see you. I mean, I don't see you yet, but it's
well,
at least good to hear your voice.
You don't really want to see me, but Yeah,
oh,
thanks.
no, I see you. So nice.
Thanks for a very interesting talk. Yeah.
Well, thank you.
So this is probably a bit tangential to what you were talking about, but have you considered how does this method work when you perhaps got some quite well structured data, but there's contamination with some very noisy outlying type of observations? Yeah, perhaps not a lot, but creating some background noise.
Yeah, it's a very good question. So what I would do is first to have like a mixture on the top. I'm discussing this also in my book, and it works kind of nice. So where you first try to separate the data between noise and kind of proper data, and then use the framework that I just presented on the kind of interesting data. So you would have like two levels of hidden indicators here. So kind of a mixture model where one of the, so first you have like these two, it's like a branch process here. So you have a first indicator that separates noise from the data, and then conditional on being in that branch, now you're using the framework here. So
okay, yeah.
And the interesting thing is you can integrate out all the indicators here. So you get like really the mixture density. And this is the important point here. When you do the clustering, the separation between signal and noise, you have just these two options, and you really use like the entire mixture density here for your proper data, and then the other components. So this is how I would approach that.
Okay, that's interesting. Thank you.
And there is another question from Angelos. Angelos, please.
Hi.
Hi, Angelos.
Can you hear me? Hi,
nice to hear
you. Not bad. Thank you. So yeah, I'm more familiar. So my question is a bit related to the previous question as well. I'm more familiar with factor models, but I think some problems are quite similar, depending also on the information from the data, like multiple modes due to non-identifiability of some parameters of these models. So do you have, and then the parameter space is, quite difficult to be summed with traditional MCMC methods. So do you have any evidence, or have you studied a bit how this telescoping sampler deals with this type of problems when there are multiple modes, smaller modes, bigger modes, and the information on the data?
Boy, that's a difficult question here. I mean, with factor models, I mean, I've been working so long with factor models. I think that the telescoping sampler could be applied there. It's just, so I do have a first project with a PhD student of mine, with Margarita, and we are trying to apply this in the context of mixture factor analysis. So like kind of first steps. I can't definitely say it is working, but it seems to be working. Now, when you say multimodality, I mean, I don't know whether you refer to the label switching problem. So the label switching problem here is not a problem because the posterior distribution of the number of clusters is invariant to the ordering, yeah, because the only thing you need are the sufficient statistics of the partition, and I don't want to go back to the slides again, but when you look at this conditional posterior of K given the sufficient statistics, it's completely invariant to the labeling problem. So estimating K plus is not prone to the label switching problem. But of course, I mean, if you want to estimate the component parameters, we have to deal with that. So we pick the mode from the posterior of K plus. We condition on that. So we stratify the MCMC draws and only keep those where we have K plus. And then we are using what I suggested in the book a long time ago. We do K-means clustering of a subset of the parameters, and that's working surprisingly well, because you don't need to resolve the clustering problem, let's say the label switching problem for the entire parameter vector. You can do it for a subset or even functionalness of that. And this is how we resolve the label switching problem.
Okay.
Yeah.
Thank you.
So I think this is in one of our papers on sparse finite mixtures, the referees forced us to explain this again in much detail. So in the appendix, you will find the details of the algorithm. But it's a very kind of hands-on method to resolve label switching. I don't know if this answered your question.
No, it answers, and I think there is this nice feature of this telescopic sampler that you can work with these sufficient statistics, right? And then you also have this problem resolved.
Absolutely, yeah. So we were so amazed how kind of easy it is that you just need the sufficient statistic from the partition, and that's it. Yeah.
Thank you very much.
So we're very looking forward to see other people pick that up, and yeah, any feedback when you're trying the sampler, the experiences you have, we would very much welcome feedback how it is working in practice. So there's always room for improvement, of course.
Yeah, sure. Thank you very much.
Thank you.
Are there any questions? I think we are done. We have to definitely try the telescopic sampler. So it's a paper out on Bayesian analysis.
Yeah, so the Bayesian analysis version is on arXiv. So there are like 3 versions on arXiv, and the most recent version is, as the paper is going to be in Bayesian analysis, it is going to appear in the December volume of Bayesian analysis. But the paper is already available on arXiv.
Great. So thank you very much, Sylvia, for the very interesting talk.
So thank you for giving me the opportunity, and it seems like, okay, with the flies and the, usually it works so smoothly, and I don't know, I still have to figure out what it has to do, but maybe there was some kind of, I mean, in the Greek mythology, there's always something happening, so it is, feels a bit like that. So really, thank you so much.
Thank you. So take care, and let's hope that we can meet each other at some point in a real conference.
That would be great. Yeah.
So all the best. Thank you very much.
Thank you all, and thank you for the nice and inspiring comments. And thank you. Bye bye.
Thank you, Sylvia. Bye.